by progressively revealing the links, assuming that 10% and then 25% and finally 50% of the links are known. In other words, instead of segmenting it or doing k-fold cross-validation, we say reveal the graph gradually. And this is more consonant with the way that users of a social network actually add friends in batches or progressively. So for every dataset DI, we find the best level, that is the best ontology level by validation for VI. Okay, so we use a validation set to find the best fixed level at which to slice. We estimate the true area under the curve for the receiver operating characteristic or specificity sensitivity curve on TI, the test set, using the best level found for the validation set. And the AUC reported for a given set of features is obtained by averaging plus or minus the standard deviation, the AUC values obtained for our 5 replications. So our classifiers include 1R, and we got expectedly poor results for 1R, so that's the last time you'll hear it mentioned. J48, or decision tree induction, random forests, support vector machines, and logistic regression. The area under the curve is the integral from 0 to 1 of the curve plotting false positive rate as the independent variable against true positive rate. So for each of the 10%, 25%, and 50% groups, we have we have one set of results. The first set for 10% shows that we have the best results for random forest, then support vector machines, then logistic regression, and finally J48, and this is borne out in the 25 and 50% data sets as well. We see from the bold face line that the training data set that consists of graph features and ontology-based numerical features, given the best level found, gives us a statistically significant, based on a paired t-test, a significantly better result than with the graph only and graph without ontology. So if we look at this, we see that there is improvement from the ontology, although the best level found, which is in parentheses at the bottom of each inducer, is not necessarily stable across the different replications, and we see that there is variation. In fact, we get different results on different runs, even though across 10%, 20%, and 25%, and 50%, we might get the same, for that particular replication, we might get the same best level. Now, if we take a look at the level of abstraction, we see a convergence. As we increase the level of abstraction from 1, which is just the root level, and pushing down, so we're basically doing top-down refinement, we see that there is a convergence towards criterion. And that reaches a point of diminishing returns as we drill down further as far as possible into the ontology. And this is forcing a fixed level of abstraction for the random forest classifier. So what have we learned and how can we extend this work? We've constructed an ontology of interest and explored its usefulness for predicting friendship links, and found that ontology-based features can be useful in link existence prediction. And this recapitulates a result that we got in earlier work that's published in the ICWSM conference, and also in still earlier, without the ontology, in our papers in ICWSM and the AAAI Spring Symposium Series 2006. In 2009, in the AAAI Spring Symposium on Social Semantic Web, we have stronger results that do look at numerical-based, ontology-based features. This also extends work that by Lisa Couture and by Bilgich on link prediction, and applies the use of metadata through concept hierarchies to improve the quality of models learned in this social network domain and in other domains such as explored by Hotho and by Zhang. We are also looking at building attribute and class value taxonomies by recursively grouping values of the attributes based on an information theoretic divergence between class distributions that are associated with our attribute values. And this is work by Kong and Punera. Punera looked at computing a similarity between class labels and building an n-array hierarchy of classes by divisive clustering. Finally, there's been work on modeling user interests by classifying the web pages that a user actually visits, and that's clickstream-based analysis. So these are the things that have been done. What we'd like to do in future work is repeat these experiments on a larger data set, 10,000 or even 100,000 users, and we already have crawls of that size. Although the actual analysis and validation, or rather extraction of the interests against our 4 WordNet and IMDb and AWS sources has not yet been done. We'd like to also predict friendship links in incomplete social networks, and most important, refine these ontologies, construct n-area ontologies, build a variable depth cut, or rather take a variable depth cut to refine the interest-based measures. And so there's no reason why we have to restrict it to a fixed depth. We can actually look at adapting the level of abstraction. And we're also looking at improved link prediction algorithms using user-defined ontologies and using other similarity measures such as cosine distance and clustering techniques such as latent semantic indexing. So this is joint work with Vikas Bahirwani and Walid Aljandal, as I've mentioned. There's another master's student from our group, Tim Wenninger, who also did a thesis on the LiveJournal social network and link existence prediction. And he actually wrote the original web crawler that collected the data for the experiments reported here. We acknowledge with gratitude the support of the National Science Foundation and Department of Defense that led to some of this research. I would be happy to receive any questions, either by email or by telephone, and thank you for your attention.